This is the Early AI podcast hosted by Seth Earley. Join us as we delve deep into the passions, expertise, and experiences of thought leaders and practitioners to talk about what's possible with artificial intelligence. The Early AI podcast is sponsored by Early Information Science, your digital transformation journey with design and deployment of innovative technology solutions, as well as Vector. Now enjoy the show.
Well, welcome to the Early AI podcast. My name is Seth Earley, and I'm your host today. On this show, we take a very practical look at how organizations are using AI to drive business outcomes, and we speak with leaders who are building the systems and the capabilities that make all of this possible. So today, we're going to be focusing on the infrastructure that's powering AI. While most conversation around AI talks about algorithms and models and application, there's really a growing need to examine the underlying compute architecture that makes these applications work, makes them scalable, makes them efficient. So joining me today is Sid Sheth, who is the CEO and co-founder of D-Matrix. They are a company that's working at the forefront of AI compute innovation. Sid has spent his career building advanced systems for high-performance workloads, and his team is now developing solutions that aim to make AI more efficient, more cost-effective, and better suited for enterprise deployment at scale. Sid, welcome to the show.
Thanks, Seth. Thanks for having me on the show.
So let's start off by thinking about this at that systems level. AI is obviously growing in complexity and scale, and it's putting more pressure on traditional compute models. So from your perspective, what are the biggest challenges that enterprises are facing when it comes to infrastructure that's needed to support AI workloads?
Yeah. No, that's a great way to start the show. I think obviously there's a lot going on with AI, and let's break this down a little bit. There's innovation happening across the AI stack. The entire tech stack, as we have known it, is being essentially rebuilt to support a different kind of compute, which is more focused on acceleration of AI workloads, right? So we lived in a world, call it from the 80s, 90s, well into the 2010s, which was focused more on scalar compute, CPU-based general purpose compute, with a tech stack that supported that type of compute. And then call it the mid 2010s, around 2015, with the arrival of AI, and a whole new class of infra had to be built to support that, which basically led to complete rebuild of the tech stack, right? At D-Matrix, obviously, we are focused on the compute layer. We are focused specifically on inference compute, not so much training. We feel, the training of AI models is something that has been well served with GPU-based solutions. And where we see most enterprises, most large-scale data center operators looking for a new class of compute to emerge is around inference. And the reason for that is inference compute in general tends to be quite different from training compute. Of course, you can use training compute to do inference, but you carry a lot of overhead that the training compute brings along with it for inference. At D-Matrix, we have essentially built a foundationally purpose-built solution for inference and inference only, without all the baggage that comes along if you were to build a training and inferencing solution. So it's essentially a very, very purpose-built solution for inference.
So say more about that. Maybe you can just talk about training versus inference. So maybe just kind of break it down for, say, a business leader to say, when we're training, what are we doing? And when we're inferring, what are we doing? And how are those different?
Yeah. I'd like to use my favorite analogy, which is, when it's not very different from us human beings. We go to school and college for the first 20 years of our life, and we educate ourselves, acquire knowledge, acquire skills, and that's, tantamount to training, right? It's training. An AI model is very similar, same concept. But then we spend the next 40 years of our life applying that knowledge. And sometimes, depending on the jobs we do, we kind of, acquire a little more knowledge. So we kind of fine tune the knowledge that we have acquired. But for the most part, we are applying the knowledge that we have acquired in school and college, and we monetize all those skills over a period of 40 years. And obviously, that's the much bigger portion of our lives. That is where we actually make our income and so on and so forth. And so it's not very different for AI. Inference is that second part. Inference is the part where you deploy a trained model. You can potentially fine tune that model for specific tasks after that. But for the most part, you're really running inference on those models. And the whole purpose is to monetize, make decisions, introduce productivity for enterprises, right? So that is the part that we are focused on, and the two are very different, right? Working is very different from going to school, and inference is very different from training, and that's where a dedicated solution makes a difference.
It's a great analogy in terms of training versus applying. And so day to day, when we are trying to apply our knowledge, we're making assumptions, we're using logic, we're deriving relationships and innovating based on understanding those patterns and understanding what is in our knowledge base and in our heads, and analogously for technology. So tell me how it's different from the infrastructure perspective. So when you said that when you have a dedicated architecture for inference versus training, what is the baggage that training brings along that you don't need in inference, and what are the things that you need in inference that you don't get in the architectures that are tuned for training?
Yeah. So at a very high level, Seth, I think it's performance versus efficiency, right? And I'll break it down for you as I answer that question. So what I mean by that is, when you look at training, training is fundamentally a performance-oriented workload, which is, so there's a lot of emphasis on scale and performance. And it's all about training a model as fast as you can train the model, because the longer it takes to train a model, the more dollars you spend. So people are trying to train it as fast as possible, which is all about performance. How quickly can you get this done? Lots of compute has to be thrown at the problem. The models, as they got bigger and bigger, you needed to support a lot of scale out. So you need to support a lot of networking across multiple. So there's thousands of GPUs these days to train an AI model, of typically a frontier model, needs tens of thousands of GPUs. So how do you take tens of thousands of GPUs with lots of compute, connect them together using a lot of networking, then build all the orchestration software to support a workload that has to be broken across all these different GPUs? They're all supposed to be kept in sync so that as the model is training, different parts of the model are all kept in sync. There is just a lot of software orchestration, a lot of networking, a lot of compute that has to be. And then, with it comes the second order challenges, which is, how do you cool all those GPUs, and how do you supply power to all those GPUs? And so the scale of the problem is a very, very different. The scale of the problem is very, very different. It's a very costly problem for most companies, and there's a lot of bleeding edge tech that has to be introduced into the solution to keep that going. Right now, inference is very, very different, because again, inference is an efficiency problem. So there, you're not necessarily building a solution with thousands and thousands of GPUs. What you're trying to do is you're taking a model that has already been trained. In many cases, you're distilling that model down. So you are actually kind of shrinking it in size. And what people are finding out, that a model that is distilled down from a very large model tends to be as capable and can do most tasks really well. So typical inference deployments from an infra perspective are like a 1 rack or a 2 rack or maybe a 4 rack deployment, unlike training clusters, which tend to be tens of racks. So the scale of the problem, the scale of the inference problem is just very different. And the reason for that is efficiency. Efficiency meaning, I need to really keep this cost optimized. I need to do more compute in less dollars. I just have a limited amount of energy. I have a limited amount of time to get this done in. So resources are very precious, and you're trying to do more inference with as few resources used. And it becomes an efficiency problem, which is why the scale of the problem kind of is very, very different compared to training.
Yeah, no, that's very helpful. And so you basically took a clean sheet approach for the most part, correct? And you designed your processors from the ground up. Is that correct?
That's right. That's exactly.
So how long did that take, and what kind of investment was that to build those? And they're called GPUs. What are they called?
We call them accelerators, just to keep it simple, right? Because people have. There is 3-letter acronyms, abound in the industry right now. People now just like to call it XPUs. We didn't want to have yet another XPU with another letter attached to it, so we're just calling it accelerators. So it's an inference accelerator. That's what we build. And your question too, how long did it take? How much money did it take? Much more than what I thought it would. Much longer than what I thought it would. Right? These, when you're building silicon and you're building hardware, it invariably turns out to be more expensive and takes more time. But yes, it was well worth the effort and well worth the money spent on it, because we took a very foundational first principles approach to inference without the baggage of having to worry about what else this solution has to do, right? So we didn't go off and build a general purpose AI accelerator. We went and built an inference only AI accelerator. And that allowed us to just make a set of trade-offs that made the solution very, very well suited for inference, right? So things like, and I'll just touch upon some of them. Things like using in-memory compute, which is a very new concept. It has been around for a while, but never been commercialized in the context of inference. Is very well suited for this platform with chiplets. Building a platform, we actually introduced new class of numerics, which are very inference friendly into the solution, which we could only do if we are doing inference, right? We are not doing training. So, there's a whole set of things we did. The way we build the software stack with open tools, because we wanted application developers to be able to program the hardware very easily. So just a bunch of decisions here that are very different and unencumbered because we just approached it from an inference perspective.
And what is the end result in terms of efficiency and cost? So when you look at, and how does an organization, leverage what you're doing? They basically have to go to a platform provider or a hyperscaler or infrastructure provider, right? They're not building their own inference infrastructure based on your chips. They're selling to a hyperscaler, and they are then providing this as part of their offerings. Yes,
that's right. So actually, this is a great segue, right? Maybe use this opportunity to show you the real product, right? So this right here is our AI accelerator, right?
Oh,
and so this is a PC. It's a PCI card today, but it doesn't have to be. We can package these chips into other types of card form factors. But today our product is a PCI card. This is a 600-watt card. You see the two chips here. The two silver boxes are the two chips. If you pop the lid on one of these chips, you'll see 4 chiplets inside each of these chips. So there's a collection of 8 chiplets on this one card right here, and there is
are those the accelerator? Do you refer to those as the accelerator?
Those are the accelerators. Yes. And there is almost 2 gigabytes of very high speed SRAM memory sitting in those accelerators, and that is almost 10 to 20 times more than what you will find from pretty much any other accelerator on the market, right? And that's only possible because of a chiplet based approach that we took. Instead of building one big monolithic chip that can go onto this card, we kind of broke it down into these 8 chiplets. And as a result of that, it became a lot more cost efficient to do it, build it because you're building smaller chips, and you're able to pack a lot more memory onto this card, right? Now, if you turn the card around, there's some DDR memory that you see at the back here, the black boxes. So there's almost 256 gigabytes of DDR memory that is sitting at the back. So there's 2 classes of memory on this card, right? There is the very fast SRAM memory. So if you want to run models that want to do ultra fast inference, you can run it from that memory. But if you care about capacity and running capacity workloads without, maybe latency is not a very big pain point for you, cost is, then you can run it out of this class of memory, right? And then what we do is we essentially take that card and then package it up into this accelerator unit. So this is the product that we ship to customers today. This is a 2 card. You can see 2 cards here, right? The one I just showed you, we have packaged 2 of those. And then we bridge it. We have bridged that to connect the 2 cards together. And from a software perspective, this is essentially the software looks at this as a single unit, right? Every chiplet, so there's a collection of 16 chiplets on these 2 accelerators. Every chiplet can talk to any other chiplet on the accelerator directly. And the software looks upon this as a monolithic model from a programming perspective. So that allows us to unlock even more efficiency and performance. So that's the product we ship, and you're absolutely right. That's our product. We don't go build the trays that the product goes into. We don't build the servers that the product goes into. We don't build the racks that the servers have to go into. We partner collaboratively with the ecosystem. There's plenty of folks who know how to build an AI server. There's plenty of folks who know how to build a rack. There's plenty of people who know how to do the cooling. We don't need any fancy cooling like liquid cooling. This is all air cooled technology. So we can work broadly with the ecosystem and essentially go fit in a customer's environment depending on what their choice of infra is. We don't dictate the kind of infra they need to build to support our solution.
And so, and again, coming back to the earlier part of the question, how do organizations leverage your technology? Do they actually purchase these accelerators and install them in, everybody's in the cloud, right? So they install it in a cloud provider, or do they rent the space from a cloud provider? How are they actually using technology and purchasing your technology?
Yeah, so our go-to market is actually quite simple, right? Of course, we have to create demand, and that is directly tied to the kind of applications that we we would really excel at, right? And the kind of applications that we really excel at is anything that requires extremely low latency. We call it ultra fast latency performance, or very high levels of interactivity. That's another way of putting it. But with batching, right? So you can support multiple users accessing an application while each user is still getting a highly interactive experience. Typically, what happens is when people start batching multiple users, they tend to sacrifice latency, right? So that is a very typical problem with GPUs. Is the moment you start putting multiple users, each user suffers in terms of their interactivity with the application. In our case, we have solved for that. We can support multiple users while each, providing a very low latency experience. So the applications that we shine at are any kind of interactive video generation, any kind of interactive coding, any kind of interactive speech so anything that requires the user to interact with AI in real time. We would really do well at that, right? And so we go to those enterprises. We actually show them the value prop of the product. We work directly with the cloud operators who know that their customers are looking for something like that. We work with sovereigns. We work with neo clouds, right? But our solution is, in some cases, our end customers are building their own infra. So we just go in with the card and sell the card to them, and they plug it into their infra. In some cases, our customers are looking for a total solution. So then we work with an ecosystem partner and go in with a total rack level solution, and then they deploy that rack level solution with our partner.
Gotcha. And what are the efficiencies? So, when you look at the market, what is the business case, and what is that level of efficiency that they're going to gain versus a traditional approach?
Yeah. So efficiency in our case, there's really three key metrics, Seth, right, that all our customers care about, right? They care about, interactivity we talked about, that is measured in milliseconds per token, right?
Yeah.
Like how quickly can you generate a token, right? And that is just, directly tied to how quickly the AI application interacts with you. The second one is cost. So that is dollars per token, right? And then the third one is energy efficiency, which is tokens per watt. Like how many tokens can you generate per watt of power, right? So really, it doesn't matter which customer we talk to on the planet. Those are the three things that they care about the most. And when it comes to our efficiency, we have done, measurement of those three key metrics. We are on latency, we shine the best. So we are like, north of 10 times better than a GPU for a certain class of applications. I'm not going to say we are, we boil the ocean here. When it comes to models that are, say 100 billion or 200 billion and less, we would be able to, be at least 10 times better on latency. We are certainly better on cost because, our hardware is so disaggregated, right?
Yeah.
So we can come into with tremendous cost efficiencies, anywhere between like 3 to 5x cost efficiency. And on energy efficiency, we are anywhere between 2 to 3x. So collectively, that is a big multiplier. That's a big multiplier. 10 times, call it 3 times 3. That is like 90x improvement, for a customer, right?
So that's pretty compelling when you think about, because obviously these things are increasing in terms of their costs and the energy demand, and all of that is certainly needs to be addressed. So when you look at the marketplace, I mean, I assume there are other people who are doing or attempting to do the stuff that you're doing, or there are similar types of solutions, but what percentage of that ecosystem of that marketplace is focusing on inference accelerators versus GPUs? That's a fair way to ask that question.
Yeah. So GPUs, I mean, it's kind of very difficult for a new entrant to come into the market at this stage, right? I mean, the GPU ecosystem has been around for decades, and obviously we have NVIDIA as a firmly entrenched GPU supplier. Yeah, just happens to be the most valuable company on the planet. That's a different story. But so I think for somebody else to come in at this stage and displace that ecosystem is going to be hard, right? So GPUs are done, right? I think really it's about inference acceleration at this point. And obviously we are entering the age of inference now, right? For the last 10 years, most of the narrative has been around training bigger models, right? As we go into the next 10 years, it's going to be about, okay, let's learn to deploy AI. Let's get an ROI. Let's talk about efficiency. Let's talk about how do we run this stuff? How do we make it useful to people? All that good stuff is going to happen in the next 10 years. And that's all about inference. And so obviously as inference heats up, a lot more companies are emerging. We are focused on inference in the data center. And in that segment, I think I would say, it's not like there's a whole lot of people, because it's an extremely capital intensive place to play. So it's not like you can start a company tomorrow and raise, you'll have to raise at least $200 million before you produce any kind of product in that space. right? So it's not for the faint-hearted.
And it's going to be a decade.
And it's going to be a decade before you really find a foothold in the market and whatnot, right? So I think it's not for the faint-hearted, and not everyone can do it. And so I think just by process of selection, that segment has less competition, right? There is just fewer players who can get started. There's there's fewer players who can keep the journey going. So many of them are dropping off. So I would say there's less than 10 people in that segment of the market who we would be competing with longer term.
And what I'm trying to get at is when you look at the infrastructure and the compute infrastructure, what percentage is being used for inference versus training, right? In other words, because what we talked about when we did our prep call is we talked about how the numbers are going to be inverted in the next several years, right?
Yeah.
So you have this very small percentage of inference and a much greater percentage. So tell me what those numbers look like, or what those percentages, or you want to qualify that market.
Right. I think today bulk of the compute, AI compute today is still pre-training, right? Just because that's where you need a lot of compute. You just need a lot of raw compute. We haven't still found the real killer application that proliferates across enterprises and proliferates across the broader ecosystem on the inferencing side just yet. It's coming. I mean, it's absolutely coming, but we are not fully there yet, right? So I would say today pre-training and training is probably 80% and inference is 20%. I've heard numbers as high as 40% on inference, and I'm not yet quite ready to believe that, but it's really about 80-20. Call it 80-20, maybe 70-30. And that is going to flip over in a span of 5 to 7 years. It's going to be probably 5 years, 50-50. And anything beyond 5 years, 7 to 10 years is going to be 20-80 flipped over, right? So
that talks about just how much this market is going to grow and explode really in the coming years, because inference is the real application of these models, right?
Absolutely.
Getting the value from a language model comes from inference, and inference compute cost right now, when it's tied to GPUs and it's tied to kind of, I don't want to say legacy infrastructure, but other models of compute, is going to be, as you say, significantly more expensive.
That's
so
right.
You're talking about, 1 or 2 orders of magnitude. As this evolves, there'll be this market force that's going to propel organizations like yours, or at least the adoption of inference as kind of a foundational architecture.
That's right. That's exactly right. Well put.
So we talked a little bit about some of the use cases. We talked about the in-memory compute a bit. Can you dive in a little bit more about how it's different than traditional architectures and why this matters for organizations who are trying to do this at scale? I know you've covered this, but maybe just dig in another level of detail.
Right. And you want me to touch a little bit more upon the in-memory computing piece, right? Yeah, for sure. Happy to. So the in-memory compute is, if you just go back to first principles and you try to understand what the inference AI workload really does, right? There is just a lot of matrix math in most of these workloads, and they need access to a lot of data. So you're kind of doing a lot of repetitive and parallel matrix compute in bulk of the dense AI models, right? There are, you're now beginning to see a lot of sparse models, but still, for the most part, there is a lot of matrix math that you got to compute, and that's just mostly repetitive parallel compute on data that you need to access from memory, right? So if you were to kind of, if you want to go find the maximum bang for your buck, and here the maximum bang for the buck comes from finding efficiency, then you would go build an engine that is most efficient at doing exactly that, right? And that's what we did. And our in-memory computing engine is exactly probably the world's most efficient matrix math engine that we built, right? And what it does is essentially, instead of typically traditional von Neumann architectures, the von Neumann architectures have compute and memory. And compute, supposing this is AI compute, and this is a matrix math engine, and there is memory sitting here, and then you are essentially pulling data from, and this is the traditional SRAM in most cases. You're pulling data from this traditional SRAM one row at a time, right? And feeding this compute engine. And there is time and energy spent in pulling that data from SRAM to keep this compute fully occupied. In our case, what we did was we just essentially co-located the compute and memory, right? We essentially built a new class of memory. Traditional SRAMs are 6 transistors. We augmented it with a few more transistors, and we made it not only a cell, but a store and compute cell. So essentially, we converted the memory into an AI computer. Right. And now what happened is that first tier of memory where you keep a lot of the model parameters are sitting inside the compute array itself, right? So you don't need to go out and fetch data from
Understood.
memory. The way we architected the memory was, instead of activating one row at a time, we can activate the whole array at a time, very similar to systolic array. So we kind of borrowed ideas from systolic architectures, from traditional in-memory computing engines, right? And we put those ideas together into something that's very unique. That saves a lot of energy, a lot of time, and it's great for inference. It's great for inference.
Yeah, and that's where your super low latency is enabled.
Correct.
I imagine you have a few patents on.
We do. We have done our best to protect the stuff we've built. Yeah.
How many patents would you
We are close to 100 patents now. Yeah.
100 patents. Wow.
Yeah.
That's a lot
Yeah.
of
Yeah.
that's a lot of IP. So when you start thinking about how enterprises, so you're getting some great resonance with investors, and the market is appreciating what you're doing, and people kind of see this. When you think about enterprises, and as their demand for AI grows, do you have specific advice you would offer to technology and business leaders who are looking at their infrastructure strategies over the next, say, 12 or 18 or 24 months? What kind of advice would you provide?
Well, I think they need to, most business leaders, at least, the conversations we are having right now, right? They're really they're still at the stage where they're trying to find out what kind of applications do they want to run on this infrastructure, right? They have they're still transitioning away from a world. Keep in mind, they lived in a world of, general purpose CPU compute, and they lived in that world for 20, 30 years, right? And now you're kind of gradually transitioning out into this new world. And that's a big leap forward. And I think GPUs are a great way to get that journey started. And that's why GPUs have been so successful. Again, my advice to most leaders would be, don't be conservative, right? Now is not the time to be conservative, and get comfortable with choice. Get comfortable with choice. I think traditional enterprises have always liked to stick with one solution, but I think in the world of inference, there isn't going to be no one size fits all. Right.
Right.
There's going to be, it is just the way the workload has been built. You're going to have different profiles of users. There's going to be multiple users trying to do different things with the workload, and there's no way you can choose one solution to serve all your needs. So the world of the future is heterogeneous, where you're going to have a compute fleet that is augmented with different types of compute to serve different needs. And technology leaders will have to get comfortable with choice. They'll have to get comfortable with choice as they go forward here.
That's great. Well, thank you so much for your time today. This has been really interesting. It's fascinating to kind of think about this from that big picture perspective, and where, infrastructure is going and how that infrastructure needs to evolve, especially when you start looking at the drivers with, increasing demand, more sophisticated models, more sophisticated applications, being able to connect different models together, be able to build out these agentic workflows, which are going to depend on inference quite a bit, and then mitigating those costs and that power consumption, as you say, by an order of magnitude. So it seems to me that this is something that leadership in enterprises needs to start to look at. Do you have any case studies right now of efficiencies where you've deployed this at the enterprise scale? Or
Yes. We are working on those, and specifically around agentic and reasoning models. Reasoning models are the underlying, AI for all agentic workflows. And I think the world of the future in the enterprise is all going to be agentic, as we all know, in the next year or two. And again, our solution is great for that, because agents care a lot about latency, because this is machine to machine communication. This is
right.
Latency matters a lot, right? And so having a solution like ours, which is extremely low latency across multiple agents, is a great fit. So yes, that's exactly the area that we're working on case studies right now with specific enterprises to kind of demonstrate the capability of what's possible, right? When you introduce a low latency solution into the agentic workflow, and how much better it would get compared to, say, a GPU-like solution.
Where can we'll have some stuff in the show notes, but where can people find you, and where can they learn more about what your offerings?
So our website is obviously a trove of information. There's wonderful information there. So www.d-matrix.ai, or you can just search for
d-matrix.ai.
Right? It's a great place to get started. We have a lot of white papers there. We have a lot of information there. please reach out to us. There is a way to reach us directly through the website, and we are very responsive, and we'll get back to you if there is any specific use cases or problems that you're trying to solve that we can help you with.
And so you're really looking for those organizations that want to innovate in this area, that understand directionally where this is going and want to be able to manage their costs, and their infrastructure as a competitive advantage.
That's right. That's exactly right.
Wonderful.
Yeah.
Well, again, thank you so much for your time today. This has been a terrific conversation. We will look forward to seeing folks in our next podcast. And again, thank you, Sid, for joining us today.
Thank you, Seth, for having me. I really, really enjoyed the conversation with you. Thank you.
That's great. This has been a great conversation about this evolving world of AI infrastructure. Again, you can find more information about D-Matrix on their website and in the show notes. If you enjoyed this episode, be sure to follow the Early AI podcast for more insights on building enterprise-grade AI applications. Thanks again.
Thank you for joining us on another deep dive into AI innovation. Tune in next time when we introduce another industry expert and discuss how to maximize AI in your world. The Early AI podcast is sponsored by Early Information Science and Vector. To learn more, visit early.com. That's EARLEY.com. Thank you for tuning in.